Okay, section 2.2, limits involving infinity. This should be very similar to what we were doing in class today, so make sure you have the notes if you're not there. So our first definition is the line y equals b is a horizontal asymptote if the function is going to some number b as I go to the left or to the right. So here we have the limit as x goes to infinity, my function is approaching b, or my limit as x goes to negative infinity, my function is approaching b. So it doesn't matter if it's doing it from the left, well, to the left or to the right, as long as it's doing one of those times, then it will be a horizontal asymptote. So say, for example, to the left it is approaching, this is your asymptote, let's say y equals 1, just to make things easy, and to the left it starts to, it thinks about it, and it doesn't, right? It's still a horizontal asymptote as long as it's doing one direction. It doesn't necessarily have to do it to the left and to the right. A vertical asymptote is as you're approaching some finite value, right, not infinity, as your x is going to some finite value from the left or from the right, then your function needs to be going to positive or negative infinity. So, example of that, we'll say that's x equals negative 1, and from the left and from the right, either it goes to positive infinity, or positive infinity, it doesn't matter, or negative infinity, as long as from at least one side, it goes to either positive or negative infinity. Okay. Here, as you go to infinity, or negative infinity, you're going to a finite number. Here, as you're going to a finite number, you're going to positive or negative infinity. Okay. In behavior models, again, we've done this in class already. We also did this in pre-calculus. But for a rational function, if I have some f of x over g of x, right, rational function is just a polynomial divided by a polynomial, then the end behavior model, in other words, what your function looks like as I go really far to the left and to the right, as I go to positive or negative infinity, is y equals the leading term of f of x divided by the leading term of g of x. Leading term meaning the terms with the highest exponents. In general, g is a right end behavior model for f if and only if the limit, if I take those two functions, so my original function is f, and then I divide it by whatever I say that my right end behavior model is, and if that limit as I go to infinity, because I'm going to the right, equals 1, then it actually works. And similarly, as I go to the left, I can divide those two functions, and if the limit as x goes to negative infinity, if g really is an end behavior model to the left, then the limit will be 1. Okay, let's do some examples that apply everything we were just talking about. So first of all, it says, find the vertical and horizontal asymptotes of the graph. Well, we need to factor the denominator. So I'll just rewrite the numerator, and I'll factor the denominator. We get 2x, we get x, and in order to get 5, that outside would be 6, and then this would be 1, so we get negative 6 plus 1 is our negative 5x. Okay, so in order to get a vertical asymptote, first we make sure that nothing's going to cancel. Remember, if we had something that canceled, then we would get a whole, but nothing cancels here. So therefore, wherever our denominator is 0, we get vertical asymptotes. So we have a vertical asymptote of x equals negative 1/2 from the 2x plus 1 set equal to 0, and then x equals positive 3 from the x minus 3 set equal to 0. Okay, each of these terms individually. Next it says, describe the behavior of the function to the left and to the right of each vertical asymptote. So I'm going to look at the limit of my function as I go to each of these. So I'm going negative 1/2. I'm approaching it from the left. Goodness, this takes forever to write. And I'm going to go to it from the right. And I'm going to do the same thing with positive 3. Okay. There are quite a few different ways that we can do this. I'm going to do the way that hopefully looks similar to what we did in pre-calculus, but you can do it numerically where you just think about what numbers you're plugging in. So say, for example, if we're doing 3 from the right, well, maybe I'll think about what would happen if I plugged in 3.1 into my function. Okay? And from the left, I would think about, oops, getting distracted. And from the left, I would think about what would happen if I plugged in like 2.9 or 2.999. 3 from the left. Last one, okay? But the way that I'm going to do it is, since I know these are going to positive or negative infinity, really all I need to do is figure out whether the sign is positive or negative, and that will be my answer. Of f of x. Whew, finally. Okay, so let's think about at 3, right? If I plug in 3.1, okay, what would happen? I would get 1 minus 3.1, which is a negative, divided by, I'll plug it into this instead of plugging into this, okay? So I just need to look at each of the terms in order to tell whether they are positive or negative. So if I plug 3.1 into this, well, obviously it's going to be positive. If I plug 3.1 into this, it's going to be positive as well. So I have a negative divided by a positive times a positive. Negative over positive is a negative, so therefore this is going to negative infinity. Okay, I could do this for all 4 of them, but remember what we did last year in pre-calculus. I think this is a little bit quicker since we have 4 limits that we want to figure out. Okay, first of all, we know the only options for it to change sign are when we have a vertical asymptote or where our function is 0. So we just make the little number line, and our function is going to be 0 whenever our numerator is 0. So if I set that equal to 0, I get x equals 1. So I just need to graph 1 and our 2 values from before, negative 1/2 and 3. So I'm going to put those in numerical order. So those are my x values. And then on top I'm going to say what my function is. So at x equals 3 and x equals negative 1/2, I get undefined. And at positive 1, it is equal to 0, right? 0 divided by anything gives me 0. Except for 0 over 0, which we don't necessarily know what that is. We'll go with undefined. So I already figured out by doing the same sign chart that I always do, as x goes to 3 from the right, it's positive, it's negative, I mean. So therefore, everywhere over here is going to be negative, right? I was approaching 3 from the right. So everything on that interval must be that same sign because I don't have any other opportunities for it to change signs, okay? In each of these intervals, the function's continuous, so it couldn't just jump into being positive without passing through 0 or having a vertical asymptote. So it is always negative. And then we can look at our multiplicities, right? If this was squared, it's of even multiplicity, so that would tell me that the signs would be the same on either side of the 3, okay? But that is not the case. We have it of odd multiplicity because it's raised to the 1, so therefore they are going to be opposite signs, okay? Same thing with my x equals 1 as my 0. I only have that once, which is of odd multiplicity, so therefore if on one side it's positive, that means that on the other side it's going to be negative. So on my graph it's just going to pass through at 1, it's not going to touch and then stay positive or stay negative. And the same exact thing over here, right? My negative 1/2, I got that just once, right? It was of odd multiplicity as well, so therefore that it has to change signs from negative to positive. So I have all 4 of my signs right here, and now I can very easily fill out the rest of these. Okay, so in general, if you don't need to do multiple limits, you don't necessarily need to do this little sign chart, but I would just do what I did down here in this first example. But if you have many of them, then it's just nice to have it all organized. Whichever way you want is fine. So 3 from the left, let me grab a different color. I'm approaching 3. From the left, it's always positive, so therefore it is positive infinity. Approaching negative 1/2 from the right, so negative 1/2 from the right is negative over here, so negative infinity. And our last one, negative 1/2 from the left, and that is positive infinity. And that's it. Next up, that was my vertical asymptotes and my limits from either side. Now we need to find an end behavior model for the function and use this to describe the end behavior. Okay, hopefully I gave you guys enough room to do this. So I want to take the leading term of the numerator, which is negative x, not necessarily just whatever term is first, divided by the leading term of the denominator, so whichever term has the highest degree. So that would be negative x divided by 2x squared. And don't forget that negative. That is still important. Let's make this blue. So our end behavior model, because it's a rational function, it's going to have the same end behavior from the left and to the left and to the right. End behavior model is going to be y equals, I'm just going to divide those two things. So negative x divided by 2x squared, and I'll just simplify. I'm going to write it as negative 1/2 times 1 over x. Of course, you could write it all together as one big fraction, but I just want to emphasize that it's just my negative 1 over x graph, and I just happen to multiply it by 1/2, so it's just half as tall as it was before. Okay. Okay, so my end behavior model looks like that. So really, who even cares about the 1/2? It's not going to change the end behavior. But what does matter is that it is negative. So my positive 1 over x would have been in the first, would have been in the first and third quadrants. But because it is negative, I lost that part. Because it's negative, we reflect it over the x or y axis. It actually doesn't matter, and it would look like this in the what is that? The second and fourth quadrants instead of the first and third. So that is what my end behavior is going to look like, right? That means that whatever this function looks like when I graph it, well, I have two vertical asymptotes here, but I don't care when we're talking about end behavior, right? The end behavior of this model is going to approach the x-axis to the left, from the positive side even, and to the right, it's going to approach the x-axis from underneath. And who cares what it looks like inside, right? We're going to have vertical asymptotes, whatever. I don't care about anything else. So, limit as x goes to infinity is 0. Also, the limit as x goes to negative infinity, it is still approaching 0. So I can actually put this all in one. The limit as x goes to positive or negative infinity equals 0. Okay. Moving on. Oh, let's say this is a different name. Good, good. I just don't want this to close on me, and I will lose part of it like I did before. Okay. Next. Same example, different function. So I have f of x equals x plus ln of absolute value of x. Okay. First I need to find the vertical and horizontal asymptotes of the graph. Oh, did I have any horizontal asymptotes from before? Yes, I did. I had a horizontal asymptote of y equals 0. I know that because of my end behavior model, because that was approaching 0. So let me stick this up here. Horizontal asymptotes of y equals 0. Sorry about that. It relates more to the end behavior model, so it makes sense to have that later. Okay. Back to this. So vertical asymptotes. Okay, well, I don't have any denominators in order to set equal to 0 in order to find a vertical asymptote, but I do have ln, right? So ln of absolute value of x, I know that I cannot take ln of 0, and I know that my ln function looks like this. Well, then what would it mean if I plug in a negative number? Well, now I'm taking the absolute value of it, so therefore it's just a reflection over the y-axis, right? If I plug in negative 2, then that's going to be the same thing as ln of positive 2, because I'm taking the absolute value first. So all these y values will be the same, regardless if I plug in the positive or the negative number. Okay, what would happen around ln of 0, right? Well, what would happen around f of 0? Huh. F of 0, well, this is going to start to go to negative infinity. This is going to get closer and closer to 0, so that's not going to really do much of anything. So my function is going to look like ln of absolute value of x, which looks like this, which is a vertical asymptote, so therefore we get a vertical asymptote of x equals 0. And just like before, we want to look at the limits as x goes to 0 from the left and from the right. Okay. So, all right, let's figure out what this one is first, and then we'll see whether or not I need to write a second one. So if I'm going from the left, okay, so from the left. From the left, what is happening to this function, right? So say I plug in 0.1, negative 0.1. Okay, well then I get negative 0.1 plus ln of positive 0.1. Okay, ln of positive 0.1, well, we're way down here. This is my ln of absolute value of x. Right, ln of very small number is down here, right? This intercept right here is at 1. So if I plug in anything that's between 0 and 1, then it's going to be this big negative number, right? Especially the smaller the x value, the more negative your ln of that value will be. So we have basically a negative infinity here plus really small negative number. Well, who cares? That is inconsequential, right? So therefore I get just ln, whoops, it's just going to look like ln of absolute value of x. So therefore that goes to negative infinity, so therefore my limit equals negative infinity. And limit as x goes to 0 from the right will be very similar. From the right, now I am plugging in positive 0.1 plus, oh look, it's still ln of positive 0.1. I take the absolute value and it's the same thing as before, and still this does not do much for us because this term completely dominates the 0.1 term. Okay, so I still have a very large negative number, so this is still negative infinity. Okay, make sure I did everything here. Vertical, done. Limit behavior, done. I'm going to go back to the horizontal. So first I need to find the end behavior model for the function, and then describe its end behavior, and then talk about any horizontal asymptotes I may have. So this one, I need to make sure that I, whether or not I have a left end behavior model and a right end behavior model. So let's look at those separately, right? Because I don't have just a rational function like before. So as x goes to infinity, what is happening to my function? Well, if I look at them separately, here's my y equals x function, here's my ln of absolute value of x function. It's a little bit sloppy, but that's okay, we get the general idea. Okay, what's happening as I go to positive infinity? Well, this is going to be exactly positive infinity, right? If whatever x value I plug in, I get that exact y value back out, right? Constant slope. And then what's happening here? Well, my slope is decreasing. My function's increasing, but my slope, it's increasing less and less as it goes along. So if I have whatever this y value is plus whatever this y value is, and I add those together, right, this is not going to make nearly as much of a difference as the x is. Okay? So therefore, as I'm going off to the right, the x is what's going to make a bigger difference. So as x goes to infinity, my right end behavior model is going to be y equals x. Let's think about it as I go to the left. Right, as I go to the left, this is going to be a negative number, right? So it's going to be negative whatever, well, it's going to be exactly the same thing as my x value, so my negative x value. And as I go to the left on my ln of absolute value of x function, yes, I'm going to infinity, but slower and slower and slower and slower. So therefore, again, this is going to make more of a difference. Does it matter the fact that this is positive and this is negative? No, because this is a small negative number relative to this is a small positive number, sorry, rather than this very large negative number. So that one makes more of a difference, and we still, when we add them together, we still get the large negative number, which is y equals x. Right? And it's already negative for us because that's what the function is there. So, therefore, my end behavior model is the same at the left and to the right. So end behavior model is y equals x. Okay. Let's check that and see. Remember before I said that something is an end behavior model if I take your original function divided by what we said was the end behavior model and take the limit either to positive or negative infinity, depending if it's a right or left end behavior model, and the limit has to be 1. So they have to do the same thing, in other words, as you go to infinity. So back to there. So now I want to take the limit as x goes to infinity first. Change this to both because I figured them both out in that one. The limit as x goes to infinity of my function. I guess I should probably write this out, huh? Oh, yeah, I definitely need to. Definitely need to because I need to divide. So I have my original function, which is x plus ln of absolute value of x, all over what I think is going to be the end behavior model, which is x. And hopefully we are going to end up with 0 after we evaluate this limit. So, as you can see, we have addition on the top, which means that I can split it apart into 2 different fractions and add those 2 limits together. So I get x over x as the first one, plus limit as x goes to infinity of ln of absolute value of x divided by x. Okay. Well, over here we can see we have x over x, and those will cancel out and just leave us with 1. Now limit as x goes to infinity of 1 is just 1, plus, well, hopefully this is 0 because we want this to end up with just 1. Ln of absolute value of x divided by x. So again, we're thinking about what does this function look like divided by x. Okay, well, as I'm going to infinity, right, because I have my limit as x goes to infinity down here, right, this is going to approach positive infinity, but slower and slower and slower. So I have a relatively small infinity. So this is a small positive number. Small positive. Divided by x. Well, right, if I draw y equals x on the same thing, right, y equals x is greater than it, so this is a larger positive number. Small number divided by a larger number is just 0, and they're both positive. 1 plus 0 equals 1. Check. Those work as an end behavior model. Okay. Limit as x goes to negative infinity. Again, I'm taking the same function and dividing it by the same end behavior model, and hopefully I will still end up with 1. And again, I'm going to break it apart into the sum of x over x. Whoop. And ln of absolute value of x divided by x. My computer's getting confused. This calculus. That's interesting. Equals, again, I can cancel this. It's just the limit of 1, which is 1, plus, this is the exact same thing as, well, very similar thing to before, right? Ln of absolute value of x. As I'm going to negative infinity this time, it's a relatively small positive number. So, little positive divided by x. Well, what is x as I go to negative infinity? That's a big negative number. Okay? So, a larger negative number. So, a small positive divided by a larger negative. Large negative. Okay? Small divided by large is going to approach 0 regardless of the signs, right? Technically it'd be like negative 0, but that's the exact same thing. So we get 1 and check. One more example. Should be very similar, and these should help you with your homework because I gave you 2 other ones with the same, almost the same exact directions. I gave you a few more directions on my own, but I did the ones that are right next to your homework questions. Last example. Okay. And this one probably will have different left and right end behavior models, so that's why I stuck this one on there. Vertical asymptote. Oh, did I do everything else over here? Too much to do. Find an end behavior model. Check. Use this to describe the end behavior. Oh, good. I didn't do that. Okay, so our end behavior is going to be the end behavior of y equals x, right? In other words, who cares what our function looks like? But as you go to the left and to the right, it is going to look like y equals x. So therefore, the limit as x goes to positive infinity is infinity, and the limit as x goes to negative infinity is negative infinity. That's infinity. And the other thing I skipped over was the horizontal asymptotes. Wow, there's a lot of directions to this. There we go. Horizontal asymptotes. Horizontal asymptotes, well, I am not approaching a number, a finite number, as I go off to the left and to the right, so therefore, no, there are no horizontal asymptotes. So let me write that up there. No HA. And I'll know what that means. And so will you. Last question. Let's save this. I feel like it's dying. Okay, vertical asymptotes. There are no vertical asymptotes for these. Awesome. No, I don't even have to do from the left and from the right. Okay, so now horizontal asymptotes we may actually have. Let's wait and see. So first let's find our end behavior model. Well, let's look at what happens if I go to the left and to the right. So as x goes to positive infinity first, what's going to happen? Well, these two functions that I'm adding together, I have y equals x squared, and I have y equals e to the negative x, which is our exponential decay function. That was a horrible graph. Aww. This one, yeah, this one, which approaches the x-axis as I go off to the right. So as I go to infinity, then this function is going to 0, this function is going to positive infinity. So my right end behavior model is just going to look like my y equals x squared. Y equals x squared. Right? Because it's just x squared added to 0, so x squared. And how about as I go to negative infinity? Well, this gets a little bit trickier because I'm adding in two different things that are going to infinity. Right? I have my y equals x squared, and then I have e to the negative x, which is increasing exponentially. So therefore, this one is going to dominate this part of the function. So therefore, my left end behavior model is equal to the exponential function, y equals e to the negative x. Okay, use this to describe the end behavior. I guess I won't prove this time. Right, you could just divide this by these ones, right? This over this would give you 1, and then the other one will give you 0, right? Same thing over here. This divided by this, x squared over e to the negative x will give you 0. E to the negative x over e to the negative x gives you 1. In either case, you have 0 plus 1 equals 1, and those check as your end behavior models. But it doesn't say to prove that, so I won't do it, because I just did in the previous one. So all I need to do is say the limit as x goes to negative infinity of f of x. Okay. Again, oops. I don't know what. Ooh. Okay. I don't really care what is happening to my function in between positive and negative infinity, but as I go off to the right, it looks like a parabola. And as I go off to the left, it looks like an exponential function, so it's increasing much quicker. Yeah, not a huge difference in those. But this is increasing quicker, this is increasing slower. Who cares? They're both going to infinity. Awesome. That means I can write it all in one thing. And then who cares what's in the middle, because that's not changing anything with our end behavior. And the last thing we need to talk about is, does it have a horizontal asymptote? Well, no, because the definition says in order to have a horizontal asymptote, you have to approach it as you go to the left or to the right, and we are doing no such thing. So no horizontal asymptotes or vertical asymptotes. And that is it for me this time. I hope you enjoyed your short notes that still had a long video.